this video, we'll be introduced to two new topics, EMF and internal resistance. Now, EMF is short for electromotive force. Now, despite the name, it technically isn't a force. This represents the drive of electrons around the circuit. So it's the amount of electrical energy transferred to a charge. Now, if this sounds familiar, it should. That's very much how we previously defined potential difference. So this is essentially the true potential difference. So as a definition, we can say EMF is the energy that is transferred or provided by a cell or battery to each unit of charge. The key difference that makes this stand out from potential difference, however, is that this is only the case when there is no current flowing. Now, the reason for this is as soon as current starts to flow through a circuit and through the cell and battery itself, it causes a heating effect, which means you never truly get the full potential of that supply. So the EMF is the true voltage of a supply, whereas the potential difference is what's actually experienced in the circuit. Now we can show this in an equation that is very similar to the potential difference equation, because of course it is. So EMF, represented by this curly E here, is equal to the energy in joules, which is the same as work done in the other equation for potential difference, over the charge Q. And naturally, EMF is given the unit V for volts. So as we said, the key difference that needs to be noticed between EMF and potential difference is the fact that when you have a current flowing, you will lose potential in the cell itself. So EMF is the energy transferred to charges by the cell or battery when there's no current, but PD represents the charge being transferred to the components in the circuit, so the actual amount of potential experienced by the circuit. Now this is all due to something called internal resistance. Now as we said, the cell heats up as current flows through it, and that's due to the resistive nature of the chemicals present in that battery. So we can call this the internal resistance of the battery. The fact it naturally will oppose the flow of electrons through it. So these collisions internally will cause the heating effect of the supply, resulting in a loss of voltage. So to define this, we can very simply state that when there is an electrical flow, or when current flows, same thing, that as the electricity flows around a circuit, that the internal resistance of the cell is essentially represented by the heating effect of that cell. And as such, we think of that as the potential difference lost across the cell itself. So that heat is the energy. And as we know, potential difference is energy per unit charge. So the term energy, or referring to it as heat, or the fact we can talk about as lost voltage, they all apply here. It's a very malleable definition to play with. But at the end of the day, really we want to represent it through the nature of an equation. So that's what we're going to do. So if we think of a circuit diagram first, we need to find a way to fully represent the difference between potential difference and EMF. So to do this, let's just start with a very simple circuit. So in this circuit, all we're going to have is a single basic component. I've chosen it for it to be a bulb, could be anything like a resistor, etc. Now, we're obviously going to make space at the top here for the cell. And where we would normally draw the cell, we can also draw a resistor next to it. So this is like a normal series circuit so far. We just happen to have a cell, resistor, and bulb in series. But if you put a dashed or dotted line around that cell and little resistor, we are indicating that this is the EMF and the internal resistance of the supply, the battery or cell, as represented by the dotted line. So that means that if we were measuring the potential difference using a voltmeter of this cell when it was disconnected on its own, we should measure the EMF. But whilst connected in this circuit, we have current flowing. So we would be measuring what is known as a terminal potential difference. So whilst the cell inside the cell, that makes sense, is the EMF, across it, the whole thing, we will have the potential difference that will be experienced, in this case, by the bulb alone. Now the internal resistance then will represent the lost volts, as it's commonly called. So the potential difference lost, used up by battery itself, so that you never experience the EMF at its full potential. So this leads us to an equation that is very simple in terms of its basis. We know that potential difference is equal to current times resistance. Well, this is a twist on that, where the EMF, our new potential difference essentially, is equal to the current multiplied by the resistance. But we'll always have the internal resistance to add on. So EMF in volts as usual, current in amps as usual. Big R represents the total resistance in the circuit that is outside the cell or source itself. So that could be any combination of components. So in our circuit above, it's the resistance of that bulb. Little r is the internal resistance of the cell or battery. And as those two resistors are essentially in series, as shown above, we're simply adding them. Now, obviously, it's quite useful to expand this equation to make proper use of it. So we can see that when we do, we end up with the EMF being equal to I big R plus I little r, where I little r is going to represent this lost voltage, this lost volts concept. So the energy wasted by heating up the battery. Now, a little aside on power supplies, it is important to realize how internal resistance can be used and controlled in our everyday lives. So normally, most things we use require a good current, a useful high current value. So, for example, if we have a torch, we don't want it heating up, we want to get the efficient output of light. A car battery needs a really high current to start. So in order not to lose energy, we need to have a low internal resistance for those supplies. However, in things like high tension or extremely high tension power supplies, we instead would end up with a potentially fatal amount of current flowing. So in order to avoid the risk to life that is presented by these situations, and especially a short circuit in those situations, we ensure that there is a high internal resistance. So no matter how high the voltage might reach, our current will be limited to very low values. So it's a clever safety feature. Now, when we consider measuring internal resistance in a practical sense, we would have to set up a circuit like the one shown. Now, all I have here is an ammeter and voltmeter to keep an eye on the current and potential difference experienced by the supply, a cell in this case. We have a variable resistor to allow us to take multiple readings, which will inevitably lead to the graph on the right. And we have a switch. Now I find a switch is a useful thing to add to these circuits simply because it allows you to take a clear, direct measurement of the EMF itself. Once connected, you could vary the variable resistor in order to get a range of results and plot them on a VI graph like this. And generally the results will be a negative gradient gradually going down like this. Now take the equation we've just had for EMF. We can link it directly to our classic VIR equation, because when it's expanded as EMF equals plus I little r, we can replace the big I r with V. So we can state that the EMF is equal to the potential difference plus the current times the internal resistance. Now you might wonder why this is useful, but this is because it allows us to link to y equals mx plus c. As we have a straight line in our graph, we can find things from the gradient and intercept. So let's plug in what we've got. We know our y-axis is potential difference, and we know our x-axis is current. So if we rearrange our equation a little bit, moving I little r over to the other side, making it a negative, we will end up with the fact that m, our gradient, is minus little r, so minus the internal resistance, and the intercept c will be EMF. So graphically, you may be expected to measure the gradient in order to find the internal resistance. Remember, it's negative here because it's a negative gradient, hence the minus cancelling out from the y equals mx plus c equation. The intercept itself is the EMF then as well. Nice and simple to measure. Thank you for your time.